Introduction to Euler's method. Euler's method, there's our old friend Euler, don't say Euler. Euler's method is a way of approximating solutions of differential equations. More precisely, initial value problems. Let's say we got an IVP that is one of the examples here. Let's take it to be this example. Let's say we want to try to approximate the purple solution curve here, which goes to the point 0, 1. It's hard to see there, but that's 0, negative 1. The differential equation with choice 1, that's t squared plus y for the right-hand side. So dy dt is f of t comma y is t squared plus 1, and the initial value was y of 0 is negative 1 for that solution that I was pointing at in purple. I want to approximate that solution without a formula. I made a mistake here. This is t squared plus y. That's pretty necessary for us at this point because we don't have any methods for solving that kind of differential equation. It's not separable. You can't separate variables. You can try, you won't be successful. You won't be able to get all the t's on one side and all the y's on the other because of the plus sign. If it were multiplication, then you could. What's the idea behind Euler's method? The idea behind Euler's method is tangent line approximations to solutions. Again, I'm trying to approximate this purple curve. Going through this point right there, that's supposed to be the point 0, negative 1. Y is negative 1 when t is 0. At that point, there's some tangent line to the curve. And the slope of the tangent line, remember, comes from the right-hand side function, f of ty. That's how you make the slope field. So use a tangent line approximation. How? The slope is a rate of change along the tangent line and approximates the rate of change along the curve. If I just take that rate of change and multiply it by the change in t, that'll give me the change in y along the tangent line. This is something you learned way back chapter 2 in calculus 1, what I just said. You may have forgotten it. Linear approximation is what I'm talking about. The textbook doesn't do this, but let me do it anyway. Euler's method is implemented by two recursive equations that generate two sequences. An application of sequences. Y sub n is going to be an approximation to the value of y along some solution curve. It equals the previous value of y, call it y sub n minus 1, plus some change in y. What I'm about to put here is the key to the method. The change in y is the rate of change of y with respect to t times the change in t. But again, the rate of change, the slope at that point is given by that function. Because that's what the differential equation is saying if it could talk to you. The slope, rate of change is given by that function at any point along the solution curve. So I need to plug in the previous point, the previous point's t and y coordinates, t sub n minus 1 and y sub n minus 1. That's from the differential equation. That really is the same as dy dt at the point tn minus 1 comma yn minus 1. That's the rate of change. To figure out the change in y, multiply that times the change in t. We're given here a step size delta t. Change in time. How big should delta t be? It's up to you. Don't choose something very big though. Don't choose 5 or 10 or anything bigger. Probably don't even choose 2 or 3 or even 1, though sometimes we do it when delta t is 1. You could pick something pretty small like 0.1. Though if you do pick 0.1, then you got to do a lot of steps sometimes in the method. That's okay. It can be implemented on a computer. You also need to update the value of t. T sub n is the previous value of t just plus delta t, plus the change in time. And the way to organize your work for this is to make a table. Make a column for n. Make a column for t sub n. Make a column for y sub n, which is the column you're most interested in, is y sub n. And make a column for f of tn comma yn times delta t. Now, don't be bothered by the fact that I'm using n as a subscript there, whereas I used n minus 1 as a subscript up there. It's not a big deal. If n is an arbitrary subscript, then n minus 1 is an arbitrary subscript as well. I used an n minus 1 up there because on the left I had an n. I could have had an n plus 1 on the left and had n's on the right. How many steps should we go? We usually don't typically like doing more than n equals 4 steps, but we could do any number of steps. We start the t value out at 0 because that's the initial value of t, 0. And then t goes up by delta t each time. Let's let delta t be 0.1, 0.1. So the next value of t is going to be 0.1, then 0.2, then 0.3, then 0.4, etc. And I can keep going. What's the first value of y? Y sub 0. It's just what you see on the right side there, -1. That goes down right there. This goes down right there. What is the method saying to do? It's saying to find the next value of y, which is going to go right where my pen is pointing at right now. Take the previous value of y and add on this quantity. So I have to figure out this quantity. F of this point, t is 0, y is -1, times delta t. How do I find that? I got to look at the formula for f. T squared plus y. 0 squared plus -1. This becomes -0.1. That now gets added to the preceding value of y. Careful, -1 plus -0.1 is -1.1, not -0.9. I'm adding these two negative numbers. Now do the same thing over again. Use the new point. T is 0.1, y is -1.1. Careful. I'm using little f again, t squared plus y. T now is 0.1, y is -1.1. That's all got to get multiplied by delta t. .1 squared is 0.01 plus -1.1 is the same as -1.1 times 0.1. This is -0.109. That gets added to -1.1, which means subtract 1.1 from this. I get a -1.209. Let's do one more step and then we'll stop. Now plug in the new point. T is 0.2. Y is -1.209. Plug it into F, multiply by 0.1. It's going to be 0.2 squared minus 1.209 times 0.1. 0.2 squared, 0.04 minus 1.209 times 0.1, negative 0.1169. That gets now added to negative 1.209, which means I can subtract 1.209 and get negative 1.3259. And then I could keep going. How long should I go? I can go to my heart's delight. If I'm after trying to approximate the solution function when t is 1, then I would want to stop when n is 10, because then t would be 1. And whatever I got there, call it y sub 10, would approximate the true solution at time 1, because that's what t is. If the true solution is called phi, it would approximate phi of 1. Though if we didn't bother using function notation, we could call this y of 1. If we didn't bother using a separate letter for the function name and just abused notation here and used y as both a dependent variable and a function name. Okay. So it can take a while to use the calculator, but we want to get some practice. On Wednesday, we'll show you how to implement this quickly in Mathematica, as well as do some applications. See you then.